The questions where we were doing two different horizontal transformations were definitely the questions where I saw the craziest stuff. People did all kinds of things. You like took the x coordinates and plugged them into this equation. Why? Because it seemed like a good thing to do. I don't know. My favorite answers were ones where people said that you're only applying horizontal transformations. You got that part right, but then you changed the y coordinates. Like that's crazy. So cool. Let's do it again. This is the time to get it. And admittedly, this is like a little bit complicated. This is probably the hardest thing that we have studied in either of these two units. So you know that the two transformations that are getting applied here are a horizontal contraction, that's the times 2, and a shift left by 1, that's the plus 1. The question was kind of which order do they happen in? So I'd suggested a particular way that you can use to think about this. You can think about the functions getting composed using our typical kind of function machine. So the f function, we don't know what the equation is, but we do know that the input 3 gives an output 2, and the input 5 gives an output 1. So for the transformed version, there's a couple of things that we're doing to the x value before it becomes an input to the f function. In particular, the first thing that happens to x is it gets multiplied by 2, and then you add 1 to it. And then that's the number that becomes the input to f. So if we want to know, let's label this point A. So we want to know in the transformed version, which x value is going to produce the point that acts like the A point in the f function. So in other words, there's some x coordinate here where we multiply it by 2 and add 1, and we get 3. And that's the x coordinate that's going to end up producing 2 as the output, because it's the x coordinate where after you apply those transformations, it's entering the f function with an input of 3. So how do you figure out what x coordinate that is? Well, you have to undo those two steps. Put a different way, you're trying to solve the equation on the inside here. If what value in 2x plus 1 is equal to 3? And so if you're solving this equation, you're undoing the steps. You're going to subtract 1 and then divide by 2. If you're thinking it backwards in the table here, if I want to figure out what x value leads to 3, work backwards. Here I'm undoing the plus 1, so that's minus 1. And then second, I'm undoing the multiplied by 2, so that's dividing by 2. So numerically, this is going to be 2, then divided by 2 is 1. And you can verify that that makes sense going forwards. So 1 times 2 gives us 2, plus 1 gives us 3. And so what that's told us is that the x-coordinate of 1 is going to end up having an output of 2 in our transformed version. So it's like this point has been sort of dilated and shifted to end up there. So how do we know what order did it happen in? Did we shift and then contract, or did we contract and then shift? The answer is given by what you've done here. So we took this point 3, and we subtracted 1, which is like a shift, and then we divided by 2, which is like a contraction. So these are telling you the two operations you're doing and the order that they're occurring in. So the way 3 gets transformed to end up to be 1 is first left shifting, then contracting. And that same story is going to apply to all the other points as well. So if I want to know in the transformed version which point acts like this 5, negative 1, I work backwards from 5. I subtract 1 to get 4. Then I divide by 2 to get 2. So here I've got the point at 2 is going to have an output of negative 1. So you can sort of, if you wanted to, try to sketch out how this all looks after you've compressed it and shifted it. I'm not going to make that attempt right now. But my point is, the same transformations occurred to this 5. We shifted it left, then we contracted it. So that's the process that you can use no matter what you're doing to figure out where these points have to end up when you transform them. And it also explains why the horizontal transformations are backwards from what you'd expect. The multiplication by 2 is actually a contraction, not an expansion. The plus 1 is actually a shift left, not a shift right. So not only are the operations the reverse of what you might expect, but they're happening in the reverse order from the order they apply to your actual input x. because when I plug in a number for x, first I multiply by 2, then I add 1. But if you're thinking about what effect that's going to have in the transformation, it's going to have the effect in the backwards order, because when you're undoing those operations to figure out what x value ends up being the input that you know, as you're undoing the operations, you undo them in the other order. So you'd subtract 1 first and then divide by 2. So that's both the process and the reason. That might have seemed like a lot of talking, but look at how fast this is to apply without all the talk. Here's kind of a similar problem. I've got y equals f of x with 2 points on it. What if I wanted to graph the transformation f of x minus 2 over 3? Well, let's have our input to the f function. We've got 7 has an output of 4. What are we doing to x before that happens? We are first subtracting 2. Let's do that here. And then we are dividing by 3. So the transformations that are applying are the ones that happen in reverse order. So first we're multiplying by 3, then we're adding 2. So where does this point get mapped to by that transformation? It's like I've got an x value of 7. I know I'm going to multiply it by 3. Why did I write plus 1 here? Sorry, all right, so 7, right, so multiplying by 3 is going to give me 21, and then adding 2 is going to give me 23. The y value is unchanged because these are only horizontal transformations. So I know that the point 23, 4 must be on the transformed graph. What about 0? So 0 is the x-coordinate. I'll multiply by 3. That's still 0. I'll add 2. That's 2. So 2, 0. So it's very fast to think about just as a mindless process. Figure out what you do to x and reverse it, and that's told you what transformations you're applying to these points. I should probably mention here at the end that all of this reasoning is not true for vertical transformations that are happening to the output of f. The output of f is your y value in the untransformed function. So all of the operations that you're applying to that output don't happen in reverse order. There's nothing weird happening. All you're doing is you're literally saying, for the new function, let's take the output from the old function, and then let's multiply it by 2, and then let's add 1. So the x-coordinates here aren't changing. The transformation is just shifting and expanding what's the y value here for, and it's doing it in that order because you can see it happening in terms of the process that's occurring with your function composition there. So that part's normal, and I think requires less explanation, and more people got that section of it. I think the horizontal transformations that are happening before you apply the function were the confusing part. Okay, I hope that that's clarified things. Good luck, everybody.